Hi, I'm Timo and I run the course Python for Structural Engineers. And in this video, I'll show you an example of how you can use Python to create nice looking structural engineering plots. I believe that with just a bit of Python knowledge, you'll be able to create really nice looking visuals really fast. The plot we'll create in this video here is this one. It's a plot showing the permissible footfall acceleration in the design of a floor slab. And this is just an example. When you can create this one, you can adapt it and you can basically change it to fit whatever visualization needs you may have. So all the code we'll be writing in our web browser using something called Google Colab, where you can write Jupyter notebooks. So it looks a bit like a Word document, but you can also write code in here. And just to give you a brief overview of how a file like this looks, you have some code, some text, and then you get down to the end, and we have the plot here. So that's what we're going to go through in this video. So all the formulas we are using here is based on the CCIP 016, a design guide for footfall-induced vibration of structures. So before we do anything, let's just import the packages that we will need. We're going to need pandas, matplotlib, numpy, and math. And we're going to set some colors that we want to use for our plot. So let's define that here. So let me just give a very brief introduction to footfall vibration. We talk about a baseline value for acceleration, and that is the value a human can just exactly feel when the floor is vibrating. If we then have a response factor of, for example, 4, that means that the acceleration is 4 times larger than that baseline acceleration. And that's what we're going to show in this plot here. The baseline acceleration is different for different frequencies of the floor. So we have this formula here where it says that under 4 Hertz, that's the baseline acceleration here. Between 4 and 8 Hertz, we have a constant value. And then if we are above 8 Hertz, we use this value here. So now using Python, it's quite simple to turn this one here into a function. So we create a function here that we call permissible acceleration. It takes the frequency as an input and a response factor with a default value of 1. So now we can write the formulas above, say that if frequency is less than 4, the baseline acceleration is this value. Under 8, it's this, and otherwise we have the last value up here, this one. And then we multiply it by the response factor and return the value. Then we define the frequencies that we want to check. We start at 0.1 Hertz, end at 100 Hertz, and we're just doing tiny steps of 0.1 Hertz. We can also increase this, but let's keep it here for now. So this here, NPA range, gonna be a list of numbers. Then we take each number in this list and run through this function. So that's what we do with this line of code that we have here. We say that we take our frequencies, and for every frequency, we calculate the permissible acceleration for that frequency. And then we also get a list here. So let's just see what we actually have now. If we start by making things a bit simple, let's just take in steps of 1. And then we can see that the frequencies are printed here. And for every frequency, we have a corresponding baseline acceleration. So now we have the 2 lists. I'm just going to change this back to 0.1 to have more data points. And now we can start using matplotlib. So we start by creating a figure. So we use matplotlib subplots here. So we create a figure and we create an axis on the figure. And then we basically just say that we want to plot the frequencies on the x-axis, the baseline acceleration on the y-axis. We want to use a dashed line, has to be black. We want to give this line the label baseline RMS acceleration for response factor 1. And we set the width to 1. The title of the plot should be this. We want to set the y label with this and the x label to frequency in Hertz. And then we get this plot here. Just zoom a little bit out so you can better see it. So yes, this is a plot, but we can definitely make some improvements to this plot if this is a template that we want to save and we actually want to have it proper looking. So the first thing we want to add to this plot is also our acceleration limit. If we have an office space, we may have an allowable response factor of 4. So we'll put that in here, 4 in here. So now we just calculate the acceleration limit using the same function as we just used before. Then we want to plot that one on the same plot. So frequencies on the x-axis, acceleration limits on the y-axis. We make it black and we give it a label with space name. That was a variable we declared in the beginning. And then we have this response factor in the label as well. We change the title of the axis to also include the space name. We add a legend. We set limits to the x-axis, we set limits to the y-axis, and then we set both the x-axis and the y-axis to logarithmic. Then we add a grid, some minor grid lines, and some major grid lines that are a bit more visible. And then we see what we get here. So already now, the plot looks a lot nicer. The last thing we could be interested in doing is to show some data points on this, because this is just the requirement to our building in this plot. And we actually also want to communicate our findings. So let's say that you have some results from your find element model. You may have some different areas of your building where your different frequencies have found the worst case acceleration. Then we can loop through these values and plot them as scatter points. So for each of these frequencies, we plot the acceleration and we label the point with office name. And then there may be some information that we want to communicate as well. It could be this point here, which is above the line, but it's okay because this is out in the corridor. No one is sitting there. So we may actually be okay with exceeding the vibration limit in one point in the building. So there we use this annotation here. We may need to fiddle a bit manually with the location of this, but it's a nice way to annotate some findings on your plot. So I hope this here gives you a bit of an idea of what you can actually do with Python. In my course, Python for Structural Engineers, I'm going to go a lot more in depth with this example and also other examples and make sure that you're able to do these things yourself. Feel free to take the code you've seen in this video and use for your own needs and adapt it as you see fit. Thanks for watching.